Hello, in this lecture we are going to discuss Langevin theory of diamagnetism, and we have already discussed the characteristic of diamagnetism. And the diamagnetism is found in those material in which electron cell is completely filled. Electron cell is completely filled, because in that situation there will be L0 as well as S0, so J will be 0, and in this situation there will be no magnetic moment. Okay, but what happens if we put a diamagnetic material in external magnetic field? What happens if we put diamagnetic material in external magnetic field? Okay, so let me take a simple model. Here is a nucleus and electron revolves around it. Okay, suppose that electron is moving anti-clockwise direction, in this direction. Okay, so at any point you can find out the direction of velocity. So this will be direction of velocity, because the tangent on the path will be direction of velocity. Okay, and suppose I put it in external magnetic field B vector. Direction of magnetic field is into the page. First, when B equal to 0 means there is no external field, in that situation electron is moving around the nucleus and feel a centripetal force, and let in initial condition when there is no magnetic field, when B equal to 0, then velocity of electron is V naught. So in this situation, centripetal force F equals to m V naught square divided by R. Okay, let this is radius and I represent it by small r. Okay, so this is equation 1. But when we switch on the magnetic field, then Lorentz force will act on the electron. Okay, and Lorentz force is given by Q V cross B. Okay, so this is electron moving anti-clockwise. Let me choose another color. So this is electron and moving anti-clockwise. Okay, this is the direction of velocity. Okay, and magnetic field is into the page. So this is the direction of velocity and magnetic field is into the page. So easily you can find out the direction of V cross B by using the right hand rule, and direction of V cross B will be towards left. This will be the direction of V vector cross B vector, but we know that charge on electron is negative, so force will be on the right direction. This will be the Lorentz force. And if the magnetic field is out of the page, in this situation V cross B will be in right direction, and the force will act in left direction. So basically what can happen, this is nucleus and this is electron. Force may act either right side or left side depending on the direction of the moving electron, either clockwise or anti-clockwise, and the direction of magnetic field into the page or out of the page. But always remember that you have to consider the magnetic field perpendicular to the plane. Okay, this is the direction of velocity. Now since there is extra force because of Lorentz force, so velocity will change, definitely change. So after applying the magnetic field, after applying the magnetic field, let velocity of electron is small v. So in this case, so in this situation or case, net force can be written as m v square divided by r and plus minus q v cross b. Since v and b are perpendicular, so vb sin theta sin 90 will be 1, and q is equals to minus of e, charge on the electron, so it will be m v square divided by r plus minus e v b. Sorry, this is v naught. Okay, this is the force before applying the magnetic field, and this is the extra force, so this is net force. Okay, and what will be the net force? Net force will be mv square divided by r. V is velocity after applying the field, okay, or you can say that this is after the Lorentz force acting on the electron. So from these two equations, here I can write mv square divided by r equals to mv naught square divided by r plus minus evb. Okay, now we know a relation, v equals to omega r, and similarly v naught equals to omega naught r. Okay, omega is frequency, this frequency after applying the magnetic field, because frequency will change, and this is the magnet frequency when magnetic field was 0, means there was no external magnetic field. So here we get m omega square r equals to m omega naught square r plus minus e omega naught b r. Okay, transfer this term here, and m r common, omega square minus plus minus e omega naught b r. Sorry, this is omega, not omega naught. Okay, this is omega, here v, not v naught. Okay, okay, so here I can use a square minus b square, so I can write it like omega minus omega naught and omega plus omega naught equals to plus minus e omega br. Now let omega minus omega naught equals to del omega and omega plus omega naught. Since there will be no much difference, no high difference between omega and omega naught, and these are two almost similar values, so I can write omega plus omega naught almost equals to 2 of omega or 2 of omega naught. Okay, so put these two values in this equation and we get mr. Omega minus omega naught will be del omega, omega plus omega naught will be 2 omega equals to plus minus e omega br. So I can cancel out it and this will be cancelled out. Okay, so here we get del omega equals to plus minus e b and 2m, and in this expression we have already discussed in our lower standard classes and graduation course. This is also called Larmor frequency expression. Okay, okay. Now in the presence of magnetic field, the magnetic moment of electron equals to EVR divided by 2. We have already obtained this expression in our first lecture. Okay, and you can put V equals to omega r, so this will be mu equals to V omega r square divided by 2. Change in magnetic moment, so I can write del mu equals to E r square divided by 2 and del omega. Now put the value from equation first, so we get E r square divided by 2 plus minus EB divided by 2m. So here we get plus minus E square r square b divided by 4m. This is change in magnetic moment, but I can call it just magnetic moment. Why I can call the change in magnetic moment? Because as we know that there is no magnetic moment initially in diamagnetic material, because in the absence of external magnetic field, diamagnetic material have no magnetic moment. Okay, now this is the change in magnetic moment after switching on the magnetic field. Since initially the magnetic moment is 0, so change in magnetic moment is actually equals to the final magnetic moment. Okay, now if I am interested to find out the average value of magnetic moment, so now average value of magnetic moment, then I can write mu equals to E square b divided by 4m, and here I can write average of r square, and I can put the sign of average here. Okay, or you just can call it mu. Why? Because change in delta mu is actually equals to mu. Okay, now r square is basically mean square distance, and I can write it like this, because in the presence of centripetal force, electron always move in a plane. Okay, this is nucleus and electron moves only a single plane, so I can write only x square plus y square. But mean square distance from nucleus, suppose I would like to write the expression in the terms of mean square distance from the nucleus, then we know that I can write it like this. Okay, now in the case of symmetry, or you can call it spherical symmetry, in that case you can assume like this. So I can write average of r square is nothing but 3 times of average of x square. Okay, and I can write it like average of 2 times of x square. So from this expression and this expression, I can put a relation between these two, small r and capital R. Okay, and what will be this relation? This is going to be average of small r square divided by 2, and I have to find out the value of small r square, so this is going to be 2 by 3 capital R square average. Okay, now we have to put this value, let this equation is 3, into equation number 2. Let me copy this equation from here. Okay, here we go. Okay, so you can call only mu or average of mu equals to, if you are talking about average, then there will be average. So this is E square, average of R square is nothing but 2 by 3 B divided by 4m, and mean distance from, this is nothing but mean square distance from nucleus, mean square distance from nucleus. Okay, so this is 2 and this will be E square B average of R square divided by 6m. This is magnetic moment. You can put both signs, plus and minus. Okay, okay, but if you read this topic in any reference book, then you will not get here a plus sign, and this is because diamagnetic material induce the magnetic moment in opposite to the external magnetic field, opposite to the external magnetic field. So you will get only a negative sign here if you read it in some reference book. I can write it like this. Okay, now this is magnetic moment because of single electron, Suppose if there are capital Z electrons in an atom, then magnetic moment. So mu, I can write it like atom equals to Z, just multiply with Z minus Z E square R square B divided by 6m. Okay, now suppose we have to find total magnetic moment of material. Okay, so what we have to do, this is magnetic moment because of single atom. So mu, you can write it like total. Okay, what I have to do, I have to just multiply it with number of atoms. Okay, now since defining a magnetic moment is not good idea for practical purpose, because the amount of material will decide the magnetic moment. So it will be better if we define magnetization. Okay, and what is magnetization? Magnetization is nothing but total magnetic moment divided by volume. So magnetization equals to minus of Z E square average of R square B divided by 6m number of atoms divided by volume. Okay, and now if I define number of atoms per unit volume equals to capital N, then magnetization will become minus n Z E square average of R square B divided by 6m. Okay, and remember that here n is not number of total atoms, n is number of atoms per unit volume. Okay, now we have to find out the value of susceptibility, that is Xi. So we know that m equals to Xi h, and h equals to B divided by mu naught. So I can write Xi equals to m divided by h or m divided by B into mu naught. Now put the value of capital M from here. So we get Xi equals to mu naught divided by B minus n Z E square average of R square. This is B, and here 6m. So we can cancel out from B to B, and xi equals to minus mu naught n z E square average of R square divided by 6m. Okay, so this is the final expression for classical Langevin theory, and it is also called classical Langevin formula for diamagnetism. Okay, so now we will study the next paramagnetism. And we have already discussed in our previous lecture about the characteristic of paramagnetic material. Since paramagnetic material have unfilled electrons, that's why there is orbital and spin contribution in magnetic moment. So paramagnetic material have their own magnetic moment, okay, but the electrons, or we can call magnetic dipoles, are oriented randomly. That's why the net magnetic moment in absence of external magnetic field is zero. In absence of external magnetic field, net magnetic moment of paramagnetic material will be zero because of their random orientation. But when we apply external magnetic field, the magnetic dipoles, or we can call them electrons, start to oriented along the external magnetic field, and they get magnetized. Okay, so this is classical theory of paramagnetism, and this is also called Langevin Curie theory. Okay, so as we know that the interaction energy of magnetic field is given by U equals to minus of mu dot B. Okay, or maybe you have remembered this minus m vector dot B vector, because we generally denote magnetic moment by small m, but here we are denoting it with mu. Okay, so this energy is going to be minus mu B and cos theta. Let this equation is equation number 1. And number of dipoles, or you can call magnetic dipoles, are given by Maxwell distribution function. Okay, and what it is? N proportional to exponential minus E divided by kT, and E is nothing but energy. Okay, K is Boltzmann constant. Okay, now if I put equals to sign, then I can write here N naught exponential minus E divided by kT, and you can write down the value of E here, N naught exponential minus, so this minus and this minus is going to be plus, so it will be going to be plus minus mu B cos theta divided by kT. Okay, I can call it equation number 2. Okay, now dn. Okay, so dn can be N naught exponential mu B cos theta divided by kT, and mu B divided by kT, and cos theta will be minus of sin theta and d theta. This is equation number 3, or we can write it like this: minus n naught mu b divided by kt exponential mu b cos theta divided by kt and sin theta d theta. Since this expression is also termed as some new amplitude, and I can write it like this: capital N naught. So this is mu b cos theta divided by kt, and this is sin theta d theta. Okay, that complete equation number 4. Okay, now we are interested to find out the average of magnetic moment. But before finding out the average of magnetic moment, just understand a simple concept. Actually, what is happening? Suppose there is some random direction of magnetic dipole. Suppose this is the direction, and this is the direction of magnetic field we are applying, and let this is angle between mu and b. So what will actually happening in paramagnetic materials, and this dipole start to align along the magnetic field. So we have to consider for the calculation of average magnetic moment the projection of magnetic moment. The projection on the direction of b vector will be mu cos theta. Again I repeat, since this is the random direction, arbitrary direction, but this dipole will oriented along the external magnetic field in paramagnetic materials, and the projection of this one on this one will be mu cos theta. So what will be average of mu cos theta? Okay, dn and dn. Okay, we can integrate it because using Maxwell equations we can find out the average of anything. Okay, so this is average of mu, this is mu cos theta. Now put the value of dn from here. So this is minus of n naught, I can put it out, exponential mu b cos theta divided by kt sin theta d theta, and same here, exponential mu b cos theta divided by kt sin theta d theta. And now understand a simple concept about the minus n naught, and we can cancel out both of these, about the limits of integration. Okay, so what will be the random orientation? Suppose this is magnetic field. Okay, so what can be the direction of dipoles? These are some random directions. Okay, all directions almost have come. So limit of angle must be from 0 to 180. 0 to 180. 180 means 0 to pi. Okay, so average of mu equals to 0 to pi mu cos theta exponential mu b cos theta divided by kt sin theta d theta, and divided by 0 to pi exponential mu b cos theta divided by kt and sin theta d theta. Now this is just simple mathematics, and I'm sure you can do it, but don't be panic, I will do it. Okay, so let mu b divided by kt equals to a, because this is not going to change, because we are integrating about the theta. So I can write some unchanged value or a constant, and let cos theta equals to x. If cos theta equals to x, then in this situation minus sin theta d theta equals to dx. Okay, and the limits, lower limit is angle theta equals to 0, so lower limit cos 0 equals to 1, and upper limit cos pi equals to minus of 1. So this is from plus 1 to minus 1, mu as it is. Cos theta can be x exponential ax, and sin theta d theta will be minus dx. So here minus, and this is dx. Okay, similarly here plus 1 to minus 1 exponential ax, and sin theta d theta can be right minus of dx. Okay, this minus and this minus will be cancelled out. So this is average of magnetic moment, magnetic moment, and we can write like this. And now this is just simple mathematics, but still I am doing it for you. Okay, you can solve this integration using u dot v isolate formula. So first function as it is, exponential ax divided by a minus exponential ax divided by a square from minus 1 to plus 1, and here it will be exponential ax divided by a from, sorry, this is limit plus 1 to minus 1. Okay, here plus 1 to minus 1. Now you can easily put the limits. I am skipping that part, and after putting the limit you will get the following expression. Okay, and just put the limits, and if you still have some problem you can ask me how to put the limits. Okay, now this is nothing but cot hyperbolic a, so I can write it like mu cot hyperbolic of a minus 1 by a. Okay, and this is the final expression. After this expression we will discuss some special cases, but in some reference book this and this function is also represented by Langevin function, and you can find it like this. Here L of a is Langevin function equals to cot of hyperbolic a minus 1 by a. So this is a magnetic moment because of one atom, and if you are doing it for n number of atoms, then you can just simply multiply it by capital N. Okay, so in that situation, and suppose capital N is number of atom per unit volume, number of atom per unit volume. In that situation this will be capital M, and this will be capital N mu cot hyperbolic a minus 1 by a. So this is magnetization. Okay, this expression, I do not have idea about the number of equations, so I simply call it equation number 5. Okay, now we will discuss some special cases. Okay, so let the first case 1, when a is very greater than 1. And what is a? You can check it here. This is a, mu b divided by kt. That means mu b divided by kt is very greater than 1, or you can write it like this: mu b is very greater than kt. So this is what the physical meaning of this expression. Actually this is representing high magnetic field, because mu b is very greater than kt. So high magnetic field and low temperature. Okay, so in this situation the magnetization will be n mu. This is exponential a plus exponential minus of a, exponential a minus of exponential minus a minus 1 by a. So if a is very greater than 1, in this situation exponential minus a will be very less than 1. So I can write it like this: n mu exponential a upon exponential a minus 1 by a, or this will be since a is very greater than 1, in this situation exponential a will be very high and exponential a will be very high. Okay, so we can put it like 1 minus 1 by a, but since a is very greater than 1, so 1 by a also can be termed 0, so we just got m equals to n mu. So this is the situation of saturated magnetization. Saturated magnetization means this is the maximum value of magnetization. It doesn't mean as you can see that there is no expression of applied external magnetic field in magnetism term. So there is, if no external magnetic field term, it means if you are increasing external magnetic field high, then there will be a case where magnetism will be saturated and magnetism will not increase beyond that limit. Okay. Now we will discuss another case second, and this is the case when a is very less than 1. A is very less than 1, it means mu b divided by kt is very less than 1, or you can write it mu b is very less than kt. So in this case temperature is high and magnetic field is low. So this is low magnetic field and high temperature case Okay, so what is the difference basically? So we know that expression of cot hyperbolic x is equals to 1 by x plus x by 3 minus x cube by 45 plus 2x5 divided by 945 and so on. This is actually an infinity series for the limits when x varies between 0 to pi, and we can already observed it that x here, x is basically representing angle, so basically x is varying from 0 to pi. So in this case cot hyperbolic x can be expanded like this series, and if a is very less than 1, so we know that if any number is less than 1, then its square, its cube and its fourth power will become very short or very small. So we can cancel out the higher order terms and we can just get these two terms. So I can write cot hyperbolic a equals to 1 by a plus a by 3 and put this value in this expression. Let me copy it from here. Come on, what the hell. Okay, here we got. So this is m capital N mu 1 by a plus a by 3 minus 1 by a. This is going to be cancelled out, and m is nothing but n mu a by 3, and you know the value of a is nothing but mu b divided by kt. So you can put the value of a here. So m equals to n mu square b divided by 3 kt. Now we have to find out the value of xi, and we know that h is nothing but b divided by mu naught. So xi equals to m divided by h, or mu naught m divided by b. Just put the value of m here. So xi is nothing but mu naught divided by B into N mu square B divided by 3 kt, and here I can cancel out B by B, and xi equals to nothing but mu naught N mu square divided by 3 kt. So this is the final expression of Langevin theory for paramagnetism, okay, for paramagnetism. But if you observe this expression, this is equals to some constant, so I can write it like this, C divided by T, and this is, you know very well, Curie law. Okay, so here is the end of this lecture.